Alright, let's go. Number 10. The relativity of simultaneity. Albert Einstein was a 26-year-old patent clerk in Bern in 1905, trying to solve a technical headache. Patent applications kept arriving for devices that synchronized railway clocks across cities, and the physics of synchronizing distant clocks kept refusing to behave the way Newton said it should. He wasn't hunting for a revolution. He was thinking about trains and lightning bolts. Newtonian physics assumed a single universal now. Every clock everywhere, in principle, could be synchronized to agree on which events happen at the same instant. Time was a shared backdrop identical for everyone, everywhere, always. Then Einstein worked through the math of two lightning strikes hitting either end of a moving train. An observer on the platform sees them as simultaneous. An observer on the train does not. Neither one is wrong. Albert Einstein published this in his 1905 paper on the electrodynamics of moving bodies in the journal Analysen der Physik, Volume 17. There is no error to correct. The disagreement is not about measurement. It is built into the geometry of space-time itself. Physicists tried to save absolute time. Hendrik Lorentz proposed an underlying aether frame where a true universal simultaneity still existed, just hidden from us, but no experiment then or since has ever detected it, and the idea survives only as an unfalsifiable add-on. Hermann Minkowski instead folded the effect directly into the geometry of spacetime in 1908, making it a structural fact, not a technical inconvenience. GPS satellites confirm it daily. Ignoring the effect would misplace your location by kilometers within hours. There is no single now spanning the universe. Someone moving relative to you, right now, has a present moment that includes events you would call your future. So whose now is the real one, and does the question even have an answer? No two clocks in relative motion have ever agreed on the present moment. Number 9. Gravitational time dilation. In 1959, Robert Pound and Glenn Rebka were not trying to reinvent time. They were graduate researchers at Harvard, attempting a technically brutal task, using the newly discovered Missbauer effect to measure an absurdly small shift in gamma-ray frequency across a 22-meter tower. General relativity predicted that clocks closer to a massive body, deeper in a gravitational well, should run measurably slower than clocks farther away. The prediction was decades old. No one had ever measured it directly in a lab. They found it. Gamma rays fired up the tower shifted in frequency exactly as Einstein's field equations predicted. A clock at the bottom of the tower ticked slower than a clock at the top. Robert Pound and Glenn Rebka published the result in Physical Review Letters in 1959, measuring a fractional frequency shift of roughly 2.5 times 10 to the negative 15th per meter of height, matching general relativity's prediction to within 10%. Later in 1971, Joseph Haffel and Richard Keating flew atomic clocks on commercial jets and confirmed it again at larger scale. GPS satellites today correct for a combined 38 microsecond daily drift caused by exactly this effect. The measurement is not in dispute. What remains unresolved is what it means. Physicists still disagree on whether time dilation reveals something about a deeper, more fundamental clock underlying all clocks, or whether time is nothing more than whatever these devices happen to read out, a purely operational fiction with no independent reality behind it. In 2010, NIST researchers led by Chow confirmed with optical lattice clocks, published in Science, that a height difference of just 1 foot produces a measurable difference in aging rate. Your head is, this instant, aging faster than your feet. Physics confirms it. Physics still can't tell you what that fact is actually a fact about. A 22-meter tower in 1959 proved your body doesn't age uniformly. Number 8. Closed time-like curves. In 1949, the logician Kurt Gödel, famous for proving that mathematics can never fully prove itself, turned his attention to general relativity as a birthday gift for his close friend and colleague Albert Einstein, then turning 70. He wasn't hunting for time travel. He was exploring exact solutions to Einstein's field equations, the way a mathematician tests the edges of a theory. General relativity was assumed to permit strange geometries, but never ones that violated basic causality. Cause always before effect, everywhere for everyone. Gödel found a solution: a universe filled with rotating matter, in which certain paths through space-time loop back and intersect their own past. Not metaphorically, mathematically, a trajectory that returns to where and when it started. Kurt Gödel published an example of a new type of cosmological solutions of Einstein's field equations of gravitation in Reviews of Modern Physics, Volume 21, in 1949. In 1974, Frank Tipler extended the result in Physical Review D, showing an infinite rotating cylinder of matter would produce the same closed time-like curves using more physically plausible ingredients. Physicists tried to dismiss it. The Gödel universe requires an infinitely large rotating cosmos our own does not resemble. The Tipler cylinder requires infinite length, which is physically unbuildable. Stephen Hawking in 1992 proposed the chronology protection conjecture in Physical Review D, the idea that quantum effects must always intervene to destroy any closed time-like curve before it can fully form. He never proved it. It remains formally a conjecture. Nothing in the equations forbids it. Only unproven physical intuition does. If the right configuration of matter ever existed, causality itself would not hold locally, and a future version of the universe could, in principle, contain a version of you meeting yourself. Nobody has proven this is impossible. They've only assumed it must be. Einstein's own equations, taken literally, do not rule out meeting your past self. Number 7. The problem of time in the Wheeler-DeWitt equation. In the 1960s, the physicist Bryce DeWitt was pursuing what seemed like the natural next step after quantum mechanics and general relativity had each proven wildly successful on their own, combine them into a single equation describing the quantum state of gravity itself, of the universe as a whole. Ordinary quantum mechanics has a Schrödinger equation, and inside it time appears explicitly, driving the system's evolution moment to moment. Any successful theory of quantum gravity was expected to preserve that basic feature. When DeWitt applied canonical quantization to Einstein's gravitational field, the time variable didn't just complicate the equation, it vanished from it entirely. Bryce DeWitt published Quantum Theory of Gravity. The Canonical Theory in Physical Review, Volume 160, in 1967, building on earlier work with John Wheeler. The result, now called the Wheeler-DeWitt equation, describes the wave function of the entire universe as static, frozen, with no time parameter driving it forward at all. Physicists have spent decades trying to reintroduce time by other means. Karel-Kucha proposed treating parts of the gravitational field itself as an internal clock. The approach works only in special, simplified cosmological models. Semi-classical approximations recover an approximate flow of time, but break down at high energies. Carlo Rovelli proposed that time is purely relational, emerging only from correlations between subsystems, with no answer for which correlations count as the clock. If the equation governing the whole universe has no time in it, then time may not be a basic ingredient of reality at all, just something that appears once you're small enough and entangled enough to be a subsystem inside it. If the universe's own wave function is frozen, why does anything inside it feel like it's moving? The equation for everything has no room in it for now. Number 6. The delayed choice quantum eraser. In 1999, Yoon-Ho Kim was a researcher at the University of Maryland, Baltimore County, working with Marlon Scully of Texas A&M to finally build a real experiment out of an idea Scully had proposed on paper 17 years earlier with Kai Doctrell. The goal was mundane by physics standards: verify a subtle theoretical prediction about entangled photons. Standard quantum mechanics says that once which path information about a particle is recorded, the wave-like interference pattern is destroyed, permanently, irretrievably, the moment the measurement happens. Kim's team erased the which path information carried by one entangled photon after its partner had already struck the detector screen and been recorded. When they later sorted the data using the erased information, the earlier recorded pattern showed interference again, as if the photon's prior behavior had been rewritten by a choice made afterward. Yoon-Ho Kim, Rong Yu, Sergei Kulik, Yanhua Shi, and Marlon Scully published Delayed Choice Quantum Eraser in Physical Review Letters, Volume 84, in 2000. Physicists moved quickly to contain the retrocausal reading. Yakir Aharonov and Suhail Zuberi argued in Science in 2005 that no usable signal can ever be sent backward through the setup. David Ellerman argued in 2015 that the experiment requires no retrocausality once you track the full correlation structure correctly. Ruth Kastner argued in Foundations of Physics in 2019 that the popular framing itself is wrong, nothing is erased, and nothing is delayed, in the sense most people assume. Physicists still don't agree with each other on what actually happened. Whether a photon behaved as particle or wave earlier in the experiment appears, in some sense determined by a choice made after the fact, even though no one disputes that no message can travel backward through time. If the past only makes sense once compared against a future choice, was there ever a fact about it before that comparison was made? An experiment finished in 2000 still can't be explained without disagreement about what before and after even meant. Number 5. Time crystals. In 2012, Frank Wilczek at MIT was working through a theoretical exercise, not an experimental one. He asked a symmetry question purely on paper. Ordinary crystals break spatial symmetry by repeating in space. Could some exotic form of matter break time symmetry instead, repeating in time all on its own, with no external driving force? Physicists quickly proved this couldn't happen in true equilibrium. In 2015, Haruki Watanabe and Masaki Oshikawa published a no-go theorem closing off Wilczek's original proposal for good. Two groups then found a loophole, not equilibrium systems. But periodically driven ones could oscillate at exactly half the frequency of the driving pulse, indefinitely, and without heating up or decaying away. Jihang Zhang, working with Christopher Monroe's group at the University of Maryland, published Observation of a Discrete Time Crystal in Nature, Volume 543 in 2017, using 10 trapped ytterbium ions. In the same issue, Soonwon Choi and Mikhail Lukin's team at Harvard reported an independent version using roughly 1 million nitrogen vacancy centers in a diamond. Skeptics pointed out these weren't true equilibrium time crystals, and the Watanabe-Oshikawa theorem still technically held. In 2018, a team led by Samali Auti observed something closer to a continuous time crystal in superfluid helium-3, blurring the line further. No one has yet resolved exactly which systems count and which don't. Matter now provably exists that ticks, on its own, with no clock outside it defining the rhythm. The material carries its own internal time structure, built into its atomic bones. If a chunk of diamond can have its own private clock, what makes you so sure yours is the only one that matters? Physicists built something that keeps its own time, independent of the universe outside it. Number 4. The entropic origin of time's arrow. In the 1990s, the mathematician Alain Connes and the physicist Carlo Rovelli were not trying to explain everyday experience. They were working through the mathematics of quantum statistical mechanics in generally covariant systems, technical territory, far from anything about memory or aging. Physics assumes a system's thermodynamic state is something that exists inside time, evolving as time passes, the way temperature changes as a pot cools. Coney and Rovelli inverted the relationship. They proposed that a flow of time doesn't come first. It is generated by a system's thermal statistical state. Time, in this view, isn't the stage. It's a byproduct. Alain Coney and Carlo Rovelli published von Neumann algebra automorphisms and time thermodynamics relation in generally covariant quantum theories in Classical and Quantum Gravity, Volume 11, in 1994. The idea forces an old problem back into view. Ludwig Boltzmann's own explanation for entropy's increase only works if the universe began in an extraordinarily low entropy state, the so-called past hypothesis, and nothing in known physics explains why it did. Roger Penrose has spent decades trying to derive that starting condition from deeper cosmological principles. In his conformal cyclic cosmology proposals, without securing broad agreement, the flow Kahn and Rovelli describe still rests on an unexplained boundary condition at the beginning of everything. If the thermal time hypothesis is right, then the sensation of time passing, the forward pull you feel reading this sentence, isn't a fundamental feature of the universe at all. It's a side effect of which corner of a mostly timeless structure you happen to be a small, thermodynamic piece of. If time is generated by heat and disorder rather than existing on its own, what was there before there was anything to generate it? Even the sense that time is flowing might be something your body is doing to you, not something the universe is doing at all. Number 3. The arrow of time and the entropy problem. In the 1870s, Ludwig Boltzmann in Vienna was trying to solve a specific technical problem, derive from the collisions of individual gas molecules, why a gas left alone always drifts toward uniform equilibrium and never spontaneously unmixes. His H theorem showed entropy should increase over time as molecules collide randomly. Matching everyday intuition perfectly, spilled milk doesn't unspill, broken glass doesn't reassemble. His own colleague Joseph Loschmidt pointed out the flaw in 1876. Newton's laws governing every individual collision are perfectly time reversible. If you could reverse the velocity of every molecule in a gas at any instant, the same laws predict entropy would decrease just as readily as it increases. Nothing in the underlying physics favors either direction. Joseph Loschmidt raised his reversibility paradox in 1876. Ernst Zermelo followed in 1896, invoking Henri Poincaré's 1890 recurrence theorem. Any bounded mechanical system must eventually return arbitrarily close to any earlier state, including low entropy ones, given enough time. Boltzmann's response was statistical rather than absolute. Entropy increases almost always, not by strict necessity, but this only relocated the mystery. It explains why entropy tends to rise from a given starting point. It cannot explain why the universe started at an improbably low entropy point in the first place. That assumption, the past hypothesis, remains bolted onto cosmology today, unproven and undissolved. Nothing in the fundamental equations of physics, not Newton's, not Maxwell's, not Schrödinger's, distinguishes future from past. The sense that time moves forward, that you age and remember and decay in one direction only, is not written into the deep laws at all. The universe's laws don't know which way is forward. Only you seem to. Physics has never located in its own equations a reason time should move only one way. Number 2. The block universe versus presentism. After Einstein's 1905 paper redefined simultaneity, his former mathematics professor Hermann Minkowski set out to give the new theory a cleaner geometric form. He wasn't debating philosophy. He was trying to simplify equations. The intuitive view, presentism, holds that only the present moment is real. The past is gone. The future doesn't exist yet. Most people live their entire lives assuming this without ever questioning it. Minkowski showed that relativity forces something stranger. Since simultaneity is relative to the observer, the present cannot be a single, universal slice of reality. Space-time is better described as one unified four-dimensional block, with past, present, and future all equally existing within it. Hermann Minkowski presented Raum und Zeit in 1908, published in the Jahresbericht der deutschen Mathematiker Vereinigung. In 1966, C.W., Rietdijk formalized the philosophical implication in philosophy of science, and Hilary Putnam extended it in the Journal of Philosophy in 1967. Because simultaneity is relative, some observer's present moment, somewhere in the universe, already contains what is your future. Philosophers tried to rescue presentism by proposing a single, privileged reference frame that defines the true present, but no experiment, ever, has found evidence for one, and adding it contradicts the core symmetry of relativity itself. C. D. Broad's compromise growing block theory keeps a real past and present while denying a real future, but can never specify what physically distinguishes the newest layer as now, rather than just another frozen slice. No experiment can currently tell block universe and presentism apart. If the block universe is correct, your birth, this exact sentence, and your death are not events that come into being one after another. They are all, permanently, already there. Is anything actually happening right now, or does it only feel that way from inside the block? No experiment has ever settled whether the future already exists. Number 1. The Boltzmann brain paradox. In the early 2000s, Lisa Dyson, Matthew Kleben, and Leonard Susskind at Stanford were working through the long-term consequences of a small measured number, the cosmological constant, the strange residual energy of empty space discovered through supernova observations in 1998. They were doing cosmology, not philosophy of mind. The expected picture of the far future is straightforward. As stars burn out and galaxies drift apart, the universe cools toward a quiet heat death, populated by whatever ordinary observer's evolution has already produced. They found something else. If the cosmological constant persists forever, the universe expands into an eternal, near-empty de Sitter state, and over infinite time, random thermal fluctuations in that near vacuum will statistically produce isolated, momentarily conscious brains, complete with false memories, far more often than any process that builds an entire evolved civilization. Lisa Dyson, Matthew Kleben, and Leonard Susskind published disturbing implications of a cosmological constant in the Journal of High Energy Physics, Volume 2002, Issue 10, Article 011. Andreas Albrecht and Lorenzo Sorbo formalized the modern version of the problem further in 2004. Proposed fixes all rest on assumptions no one can currently test. Don Page and Sean Carroll have argued de Sitter vacua may decay before Boltzmann brains can form in significant numbers. Alan Guth and Alexander Vilenkin have proposed specific probability measures across an eternally inflating multiverse that suppress the count, chosen, critics note, partly because they give the answer we want. String theory's swampland conjectures now question whether a truly eternal de Sitter universe is even mathematically consistent at all. If the standard cosmological model holds and none of these fixes are correct, then a typical self-aware observer in the universe's future is overwhelmingly more likely to be a randomly assembled fluctuation with implanted memories of a life it never lived than someone with an actual evolutionary history behind them. If you can't rule out being that fluctuation, on what basis exactly? Do you trust the memory you just had of reading this sentence? 10 separate lines of physics, and every single one leads back to the same quiet unraveling. The universe is not confused about time. We are. Simultaneity, entropy, quantum erasure, the frozen equation at the bottom of quantum gravity, none of these anomalies live at the fringes of some fringe theory. They sit at the exact center of our most rigorously tested physics, the equations behind GPS satellites and nuclear power plants, and every gadget in your pocket. We built a civilization on top of theories that cannot agree on whether time is even real. And if they can't agree on that, they can't fully guarantee that the you reading this sentence is standing where, or when, you think you are. If you want to see more videos like this, click the video on screen now.